Okay, so in today's video, I'll be explaining counting and probability AoPS challenge problem 5.20. The problem states, in this problem, people and desks are distinguishable, but books are not. So this is a classic indistinguishable and distinguishable problem, kind of. In how many ways can three people be seated at a row of five desks, one person per desk? Since the people are different, order matters. Combinations. Order doesn't matter. Permutations mean order does matter. So these two are really important facts that you have to memorize and understand why. Well, if you forget it in the middle of some competition, just remember that the one that's smaller tends to be the one that has more limits to it. We permute. 5 times 4 times 3 equals 60 ways. Okay, so this problem is quite easy, and 5.20 is easy if you understand permutations and combinations and distinguishability. But the thing you want to take away from this problem is combinations mean order doesn't matter, and permutation means order does matter. B reads, in how many ways can three identical copies of this textbook be placed on a row of five desks such that no desk has more than one book? Order doesn't matter here, as books are identical and people aren't anything here. Combinations means five desks, and we choose three of them for our copies of the book to be placed on it. And as I said before, combinations means order does not matter. 5 choose 3, simple combination problem, so it's 10. This problem's, again, also easy as the first problem, but you just have to understand combinations and permutations, and you'll get this one. The last one is slightly harder. What is the answer to be if you allow more than one book on each desk? So now, see, we allow one book, two books, and three books. So our three cases will be all books on different desks, next two books on together, and next one is three books on one desk. So, first case, this is the answer to part B, as if you remember for part B, it says, if in how many ways can three identical copies of the book be placed on a row of five desks such that no desk has more than one book? So this basically means that every book's on different desks. So it's the same answer as part B. The second case is pick a desk for the first two books, because you want one desk to have two books and the other desk to have one book. So when you choose what desks you have for the first two books, there's five choices because you don't have any desks chosen yet. The last one, well, the third book, you have four choices since you can't pick the one of the two books. Of course, you can also pick the lone book by itself first, and then the books that are together second. But it's really the same thing as you multiply the cases, so it's 5 times 4 equals 20. Third case is three books on one desk. So really what you want to count for this one is every desk, the desk amount, because you don't choose the books anymore. You know they have to stay on one desk, and the amount of desks is like chosen, and they told you that at the beginning of part A. There's only five desks, so the answer would be obviously 5. As these are all cases in one problem, you will like to add them. So it's 10 plus 20 plus 5, which you will get 35 arrangements. All right, so to summarize, what you want to know first is how to casework. Based on this problem, we caseworked all books different desks, second, two books together, and lastly, three books on one desk. Next, you also want to know permutation and combinations. What's the difference? Permutations means order does matter, while combinations means order doesn't matter. All right, so knowing this, have a great day and thanks for watching.